Light rail. The light rail transit is urban public transport using rolling stock similar to a tramway, but operating at a higher capacity, and often on an exclusive right-of-way. There is no standard definition, but in the United States, where the terminology was devised in the 1970s, light rail operates primarily along exclusive rights-of-way and uses either individual tramcars or multiple units coupled to form a train. A few light rail networks tend to have characteristics closer to rapid transit or even commuter rail. Some of these heavier rapid transit-like systems are referred to as light metros. Other light rail networks are tram-like in nature and partially operate on streets. Light rail systems are found throughout the world, on all inhabited continents. They have been especially popular in recent years due to the lower capital costs and increased reliability compared to heavy rail systems. Definition: the term light rail was coined in 1972 by the U.S. Urban Mass Transportation Administration to describe new streetcar transformations that were taking place in Europe and the United States. In Germany, the term Startbahn was used to describe the concept, and many in the UMTA wanted to adopt the direct translation, which is city rail. However, the UMTA finally adopted the term light rail instead. Light in this context is used in the sense of intended for light loads and fast movement, rather than referring to physical weight. The infrastructure investment is also usually lighter than would be found for a heavy rail system. The Transportation Research Board defined light rail in 1977 as a mode of urban transportation utilizing predominantly reserved but not necessarily grade-separated rights-of-way. Electrically propelled rail vehicles operate singly or in trains. LRT provides a wide range of passenger capabilities and performance characteristics at moderate costs. The American Public Transportation Association, in its glossary of transit terminology, defines light rail as ... a mode of transit service operating passenger rail cars singly on fixed rails in right-of-way that is often separated from other traffic for part or much of the way. Light rail vehicles are typically driven electrically, with power being drawn from an overhead electric line via a trolley or a pantograph driven by an operator on board the vehicle, and may have either high platform or loading or low-level boarding using steps. Quote, however, some diesel-powered transit is designated light rail, such as the O-Train Trillium Line in Ottawa, Canada, the River Line in New Jersey, United States, and the Sprinter in California, United States, which use diesel multiple-unit cars. Light rail is similar to the British English term light railway, long used to distinguish railway operations carried out under a less rigorous set of regulation using lighter equipment at lower speeds from mainline railways. Light rail is a generic international English phrase for these types of rail systems, which means more or less the same thing throughout the Anglosphere. The use of the generic term light rail avoids some serious incompatibilities between British and American English. The word tram, for instance, is generally used in the UK and many former British colonies to refer to what is known in North America as a streetcar, but in North America tram can instead refer to an aerial tramway or, in the case of the Disney amusement parks, even a land train. The word trolley is often used as a synonym for streetcar in the United States, but is usually taken to mean a cart, particularly a shopping cart. In the UK and elsewhere, many North American transportation planners reserve streetcar for traditional vehicles that operate exclusively in mixed traffic on city streets, while they use light rail to refer to more modern vehicles operating mostly in exclusive rights-of-way. Since they may operate both side by side targeted at different passenger groups. The difference between British English and American English terminology terminology arose in the late 19th century when Americans adopted the term street railway rather than tramway, with the vehicles being streetcars rather than trams. Some have suggested that the Americans' preference for the term street railway at that time was influenced by German immigrants to the United States, as it is the same as the German term for the mode, Straßenbahn. A further difference arose because, while Britain abandoned all of its trams except Blackpool after World War II, 7 major North American cities continued to operate large streetcar systems. When these cities upgraded to new technology, they called it light rail to differentiate it from their existing streetcars, since some continued to operate both the old and new systems. Since the 1980s, Portland, Oregon, has built all 3 types of system: a high-capacity light rail system in dedicated lanes and rights-of-way, a low-capacity streetcar system integrated with street traffic, and an aerial tram system. The opposite phrase, heavy rail, used for higher capacity, higher speed systems, also avoids some incompatibilities in terminology between British and American English, as for instance in comparing the London Underground and the New York City subway. Conventional rail technologies including high-speed, freight commuter, regional, and metro, subway, elevated urban transit systems are considered heavy rail. People movers and personal rapid transit are even lighter, at least in terms of capacity. Monorail is a separate technology that has been more successful in specialized services than in a commuter transit role types. Due to varying definitions, it is hard to distinguish between what is called light rail and other forms of urban and commuter rail. A system described as light rail in one city may be considered to be a streetcar or tram system in another. Conversely, some lines that are called light rail are in fact very similar to rapid transit. In recent years, new terms such as light metro have been used to describe these medium-capacity systems. Some light rail systems, such as Sprinter, bear little similarity to urban rail, and could alternatively be classified as commuter rail or even intercity rail. In the United States, light rail has become a catch-all term to describe a wide variety of passenger rail systems. There is a significant difference in cost between these different classes of light rail transit. Tram-like systems are often less expensive than metro-like systems by a factor of 2 or more. Lower capacity. The most difficult distinction to draw is that between light rail and streetcar or tram systems, there is a significant amount of overlap between the technologies. Many of the same vehicles can be used for either, and it is common to classify streetcars or trams as a subcategory of light rail rather than as a distinct type of transportation. The 2 general versions are the traditional type, where tracks and trains run along the streets and share space with road traffic. Stops tend to be very frequent, but little effort is made to set up special stations. Because space is shared, the tracks are usually visually unobtrusive. A more modern variation, where the trains tend to run along their own 50 feet right-of-way and are often separated from road traffic. Stops are generally less frequent, and the vehicles are often boarded from a platform. Tracks are highly visible, and in some cases significant effort is expended to keep traffic away through the use of special signaling, level crossings with gate arms, or even a complete separation with non-level crossings. Higher capacity. At the highest degree of separation, it can be difficult to draw the line between light rail and metros, as in the case of Wuppertal's Schwebebahn hanging rail system, a branch of Boston's Green Line, or London's Docklands Light Railway, which would likely not be considered light were it not for the contrast between it and the London Underground. Many consider these not to be light rail lines but light metros. However, in Europe, The term light rail is increasingly used to describe any rapid transit system with a fairly low frequency of short trains compared to heavier mass. Rapid systems such as the London Underground are Singapore's mass rapid transit. For instance, the LRT-1 and MRT-3 in Manila are often referred to as light rail, despite being fully segregated, mostly elevated railways. This phenomenon is quite common in Chinese cities, where elevated light metro lines in Shanghai, Wuhan, and Dalian are called light rail lines. In North America, such systems are not considered light rail. Mixed systems. Many systems have mixed characteristics. Indeed, with proper engineering, a rail line could run along a street, then go underground, and then run along an elevated viaduct. For example, the Los Angeles Metro Rail's Gold Line light rail has sections that could alternatively be described as a tramway, a light metro, and, in a narrow sense, rapid transit. This is especially common in the United States, where there is not a popularly perceived distinction between these different types of urban rail systems. It is even possible to have high-floor rapid transit cars run along a street, like a tram. This is known as street running. Speed and stop frequency. In some areas, light rail may also refer to any rail line with low speeds and many stops in a short distance. This inherits the old definition of light railway in the UK. Hong Kong's light rail is an example of this, although it is also called light rail because it is a lower scale system than the rest of the MTR. Sprinter in the San Diego area uses DMUs and is targeted towards a commuter rail audience. However, because of the large number of stops along the line, it is called light rail. Reference speed from major light rail system is shown below. However, low top speed is not always a differentiating characteristic between light rail and other systems. For example, the Siemens S70 LRVs used in the Houston Metrorail and other North American LRT systems have a top speed of 106 km per hour, while the trains on the all-underground Montreal Metro can only reach a top speed of 72 km per hour. Los Angeles Metro light rail vehicles have higher top and average speeds than Montreal Metro and New York subway trains. The main difference is that Montreal Metro and New York subway trains carry far more passengers than any North American LRT system, and the trains have faster acceleration, making station-to-station times relatively short in the densely populated urban areas. Most light rail systems serve less densely populated cities and suburbs where passenger traffic is not high, but low cost combined with high top speed may be important to compete with automobiles. System-wide considerations. Many light rail systems, even fairly old ones, have a combination of both on- and off-road sections. In some countries, only the latter is described as light rail. In those places, trams running on mixed rights-of-way are not regarded as light rail, but considered distinctly as streetcars or trams. However, the requirement for saying that a rail line is separated can be quite low, sometimes just with concrete buttons, to discourage automobile drivers from getting onto the tracks. Some systems such as Seattle's Link are truly mixed but closed to traffic, with light rail vehicles and traditional buses both operating along a common right-of-way. Some systems, such as the AirTrain JFK in New York City, the DLR in London, and Kelana Jaya Line in Kuala Lumpur, Malaysia, have dispensed with the need for an operator. The Vancouver SkyTrain was an early adopter of driverless vehicles, while the Toronto Scarborough Rapid Transit operates the same trains as Vancouver, but uses drivers. In most discussions and comparisons, these specialized systems are generally not considered light rail. History. Many original tram and streetcar systems in the United Kingdom, United States, and elsewhere were decommissioned starting in the 1950s as the popularity of the automobile increased. Britain abandoned its last tram system, except for Blackpool, by 1962. Although some traditional trolley or tram systems exist to this day, the term light rail has come to mean a different type of rail system. Modern light rail technology has primarily West German origins, since an attempt by Boeing Vertol to introduce a new American light rail vehicle was a technical failure. After World War II, the Germans retained the streetcar networks and evolved them into model light rail systems. Except for Hamburg, all large and most medium-sized German cities maintain light rail networks. The basic concepts of light rail were put forward by H. Dean Quinby in 1962 in an article in Traffic Quarterly called Major Urban Corridor Facilities, a New Concept. Quinby distinguished this new concept in rail transportation from historic streetcar or tram systems as having the capacity to carry more passengers, appearing like a train, with more than one car connected together, having more doors to facilitate full utilization of the space, faster and quieter in operation. The term light rail transit was introduced in North America in 1972 to describe this new concept of rail transportation. The first of the new light rail systems in North America began operation in 1978 when the Canadian city of Edmonton, Alberta, adopted the German Siemens Duewag U2 system, followed 3 years later by Calgary, Alberta and San Diego, California. The concept proved popular, and although Canada has few cities big enough for light rail, there are now at least 30 light rail systems in the United States. Britain began replacing its run-down local railways with light rail in the 1980s, starting with the Tyne and Wear Metro and followed by the Docklands Light Railway in London. The historic term light railway was used because it dated from the British Light Railways Act 1896. Although the technology used in the DLR system was at the high end of what Americans consider to be light rail, the trend to light rail in the United Kingdom was firmly established with the success of the Manchester Metrolink system in 1992. Track gauge. Historically, the track gauge has had considerable variations, with narrow gauge common in many early systems. However, most light rail systems are now standard gauge. Older standard gauge vehicles could not negotiate sharp turns as easily as narrow gauge ones, but modern light rail systems achieve tighter turning radii by using articulated cars. An important advantage of standard gauge is that standard railway maintenance equipment can be used on it, rather than custom-built machinery. Using standard gauge also allows light rail vehicles to be moved around conveniently using the same tracks as freight railways. Another factor favoring standard gauge is that accessibility laws are making low-floor trams mandatory, and there is generally insufficient space for wheelchairs to move between the wheels in a narrow gauge layout. Furthermore, standard gauge rolling stock can be switched between networks either temporarily or permanently, and both newly built and used standard gauge rolling stock tends to be cheaper to buy, as more companies offer such vehicles. Comparison to other rail transit modes. With its mix of right-of-way types and train control technologies, LRT offers the widest range of latitude of any rail system in the design, engineering, and operating practices. The challenge in designing light rail systems is to realize the potential of LRT to provide fast, comfortable service while avoiding the tendency to over-design that results in excessive capital costs beyond what is necessary to meet the public's needs. Typical rolling stock. The BAT rail car in the following chart is not generally considered to be a light rail vehicle, and is only included for comparison purposes. Train operation. An important factor crucial to LRT is the train operator. Unlike rail rapid transit, which can travel unattended under automatic train operation, safe, high-quality LRT operation relies on a human operator as a key element. The reason that the operator is so important is because the train tracks often share the streets with automobiles, other vehicles, and pedestrians. If trains were fully automated on roads, nobody would be there to stop the train if a car pulled in front of it. Light rail trains are actually very sturdily built for passenger safety, and to reduce damage from impacts with cars. Floor height. The latest generation of LRVs has the advantage of partially a fully low floor design, with the floor of the vehicles only 300 to 360 mm above the top of the rail, a feature not found in either rapid rail transit vehicles or streetcars. This allows them to load passengers, including those in wheelchairs or strollers, directly from low-rise platforms that are little more than raised sidewalks. This satisfies requirements to provide access to disabled passengers without using expensive and delay-inducing wheelchair lifts, while also making boarding faster and easier for other passengers. Power sources. Overhead lines supply electricity to the vast majority of light rail systems. This avoids the danger of passengers stepping on an electrified third rail. The Docklands Light Railway uses an inverted third rail for its electrical power, which allows the electrified rail to be covered and the power drawn from the underside. Trams in Bordeaux, France, use a special third rail configuration where the power is only switched on beneath the trams, making it safe on city streets. Several systems in Europe and a few recently opened systems in North America use diesel-powered trains, tram and light rail transit systems worldwide. Around the world there are many tram and streetcar systems. Some date from the beginning of the 20th century or earlier, but many of the original tram and streetcar systems were closed down in the mid-20th century, with the exceptions of many Eastern Europe countries. Even though many systems closed down over the years, there are still a number of tram systems that have been operating much as they did when they were first built over a century ago. Some cities that once closed down the streetcar networks are now restoring, or have already rebuilt, at least some of the former streetcar tram systems. Most light rail services are currently committed to articulated vehicles like modern LRVs, i.e. trams, with the exception of large underground metro or rapid transit systems. Capacity. Efficiency. The table below illustrates the capacity of a light rail train compared to that of a standard car with 5 seats. The average length of a standard 5-seat car is about 4.74 meters. The length of a Siemens S70 light rail vehicle is 27.7 meters, approximately the same length as 5.8 cars. The maximum occupancy of a car is 5 people. The maximum capacity of the Siemens S70 is 220 people. This means that 1 meter in a car has a capacity of 1 person, and 1 meter in a light rail vehicle has a capacity of almost 8 persons. So the capacity of light rail is about 8 times higher than that of a car, if only the length of the vehicles is taken into consideration. The average width of an automobile is about 1.77 meters, while the average width of the Siemens S70 is about 2.7 meters. The area of a car is about 8.4 square meters, while the area taken up by a light rail car is about 74.8 square meters. In a car, each square meter has room for only 0.6 persons, while each square meter in a light rail car has room for 2.9 persons. This This means that a light rail is significantly more capacity effective than a car. Height is not taken into consideration, because it is not normally a problem given minimum clearance regulations for underpasses. Energy efficiency for light rail may be 120 passenger miles per gallon of fuel, but variation is great depending on circumstances. Comparison with high-capacity roads. While the table above compares the maximum capacity of each mode, the average use of a lane might be quite different based on a number of factors. One line of light rail has a theoretical capacity of up to 8 times more than one 12-feet lane of freeway during peak times. Roads have ultimate capacity limits that can be determined by traffic engineering. They usually experience a chaotic breakdown in flow and a dramatic drop in speed if they exceed about 2,000 vehicles per hour per lane. Since most people who drive to work or on business trips do so alone, studies show that the average car occupancy on many roads carrying commuters is only about 1.5 people per car during the high-demand rush hour periods of the day. This combination of factors limits roads carrying only automobile commuters to a maximum observed capacity of about 3,000 passengers per hour per lane. The problem can be mitigated by introducing high-occupancy vehicle lanes and ride-sharing programs. But in most cases the solution adopted has been to add more lanes to the roads. By contrast, light rail vehicles can travel in multi-car trains carrying a theoretical ridership up to 20,000 passengers per hour in much narrower rights-of-way, not much more than 2 car lanes wide for a double-track system. They can often be run through existing city streets and parks, or placed in the medians of roads. If run in streets, trains are usually limited by city block lengths to about 4 180 passenger vehicles. Operating on 2-minute headways using traffic signal progression, a well-designed 2-track system can handle up to 30 trains per hour per track, achieving peak rates of over 20,000 passengers per hour in each direction. More advanced systems with separate rights-of-way using moving block signaling can exceed 25,000 passengers per hour per track. Practical considerations. Most light rail systems in the United States are limited by demand rather than capacity, but Boston's and San Francisco's light rail lines carry 9,600 and 13,100 passengers per hour per track during rush hour. Elsewhere in North America, the Calgary C-Train and Monterey Metro have higher light rail ridership than Boston or San Francisco. Systems outside North America often have much higher passenger volumes. The Manila Light Rail Transit System is one of the highest capacity ones, having been upgraded in a series of expansions to handle 40,000 passengers per hour per direction, and having carried as many as 582,989 passengers in a single day on its line number 1. It achieves this volume by running 4-car trains with a capacity of up to 1,350 passengers each at a frequency of up to 30 trains per hour. However, the Manila Light Rail system has full grade separation and as a result has many of the operating characteristics of a metro system rather than a light rail system. A capacity of 1,350 passengers per train is more similar to heavy rail than light rail. A bus rapid transit system using dedicated lanes can have a theoretical capacity of 3,600 passengers per hour per direction. BRT is an alternative to LRT, at least if very high capacity is not needed. Using buses, roads can achieve a much higher commuter capacity than is achievable with passenger cars. To have 30 buses per direction an hour, buses must have priority at traffic lights and have their own dedicated lanes. Buses can travel closer to each other than rail vehicles because of better braking capability. However, each bus vehicle requires a single driver, whereas a light rail train may have 3 to 4 cars of much larger capacity in one train under the control of one driver, or no driver at all in fully automated systems, increasing the labor costs of high-traffic BRT systems compared to LRT systems. The peak passenger capacity per lane per hour depends on which types of vehicles are allowed at the roads. Typically, roadways have 1,900 passenger cars per lane per hour. If only cars are allowed, the capacity will be less and will not increase when the traffic volume increases. When there is a bus driving on this route, the capacity of the lane will be more and will increase when the traffic level increases. And because the capacity of a light rail system is higher than that of a bus, there will be even more capacity when there is a combination of cars and light rail. Table 3 shows an example of peak passenger capacity.